Okay. Okay. Okay.
Mm-hmm. We can see.
Okay. Okay. Well, good morning, everybody. Uh, Today I going to talk about the nowhere differentiability of the Brownian motion. So, the content of my talk. First, I will start with some brief definitions, and then I will give you the principal theorem. So we start with Dini derivatives. Well, for a continuous function from the non-negative uh, numbers to the real numbers, we denote the upper right and left Dini derivatives of t by this. Okay, the line sub when h tends to 0 by right and left of this quotient. In the same way, you can define the lower right and left Dini derivatives of t by this, no? The limit when h tends to 0 by left and right of this quotient. Just to remember, for instance, here we have the lower right derivative of if at t, well, is a limit when h tends to 0 by right of this quotient, but this is equal to this, okay? Is the limit when delta tends to 0 by right of the infimum, taking over all the h between this interval from 0 to delta of this quotient. Okay, just to remember. Uh, Also, you can express that limit like this. The limit when k tends to plus infinite uh, of the infimum of this function g of h, where h is in this interval, and this is the function j of h. Okay. Mhm. Then I will come back to this definition later. So, uh, we have that a function f is differentiable at t from right if the lower uh, if the upper and lower right derivatives are equal and also are finite numbers. The function is differentiable at t from left if the uh, upper and lower left Dini derivatives are finite numbers and are equal. And finally, we said that a function f is differentiable at some t positive if it's differentiable from both the right and the left, and the four Dini derivatives agree. So, if one of the Dini derivatives, for instance, is I don't know, infinite, so the function will not be differentiable at t. Okay. From the definition is it's obvious that this happens, no? And also you can have this just by definition because one is the limit and the other is the lim sub. Sorry, here is this. Well, now I'm going to present the principal and unique theorem of my talk. This theorem is due to Pali, Wiener, and Simon around 1933. It speaks about the no differentiability of the Brownian motion. Well, it says that for almost every little omega in omega, the Brownian sample path W as a function of t is nowhere differentiable, and more precisely, the set A, okay, the set where for each t non-negative, a real number, either the upper right derivative of the Brownian motion is infinite plus infinite, or the lower right derivative at t of the Brownian motion is minus infinite. Okay, so we will prove that this set A contains an event f measurable with full probability. Okay. But
Okay, just let me say that this implies that we can say that the probability of A is equal to 1, because unless of set of measures 0, if we have made the
okay, I was
if the probability is complete, then we can say that the probability of A is equal to 1.
okay. Yes, I was thinking about that. Actually, we are going to work with the complement of this set. We will find a set measurable, a null set, okay, with probability 0. But we are working in a complete probability space. For that reason, this set also is measurable and with probability 0. Okay.
Yes.
Yes. Yes. Actually, we will work with the complement. Okay. So note that this event A implies this other event D, where the Brownian motion is not differentiable at t. Okay, because if one Dini derivative is not a real number, so the function is not differentiable at t. Okay, so to begin with the proof, it's enough to consider this interval as the proof that we saw before. Let's fix j greater or equal than 1 and k greater or equal than 1. And we will define the set. Okay, this set is where exists a t between 0 and 1, such for all h between 0 and 1 over k, we have this quotient. We have this quotient bounded by j. Okay. So now that the complement of this set is included in this set V, where V is where the lower right Dini derivative is greater than minus infinite, and the upper right Dini derivative of the Brownian motion is less than plus infinite for some t. Okay, these inequalities by definition, and the other are by, well, we are taking complement, okay, of this set. So here we are working with a complement of the set A, okay, but here I going to correct something. Here is from 0 to 1 because we will be working in this interval, okay. Now I'm going to decompose this set V like this, okay. V can be expressed like the union over all j from 0 from 0 to infinite of the union over all k from 0 to infinite of these events a, j, k, okay. Now our objective, in order not to get lost, our objective is to prove that this set has probability 0, okay. And for that we will show that this set has probability 0. To see just to see why this equality holds, I'm going to speak a little about why this equality holds. Well, know that the set V is where the right lower and upper derivatives are between real numbers, right? Are real numbers. In this set, A, J, K is a set where this quotient is bounded in certain neighborhood. Okay. So if this quotient is bounded in by above and by below in this neighborhood, like a function of h, so the lim sub and the lim if also will be bounded. Okay. That's the reason. Just remember the definition here, no? Okay. Now my objective is to prove that this event has probability 0. Okay. For that, we will find a measurable set that contains this set AJK with probability 0. Okay. So indeed, if the event AJK happens, what we have? We have that exists a t between 0 and 1 with this for all h in the interval from 0 to 1 over k. No, just by definition of AJK. Okay, just by definition. Now now well, remember that the k is fixed, right? K is fixed. K is fixed, so we can take an integer n greater or equal than 4 times k. Okay, I'm going to do a graph. We have t between 0 and 1, and we are going to divide this interval in subintervals. This one is n over n. I'm going to divide like this. That's the idea. Okay. So is it possible to find an integer ai between 1 and n with this property? Okay. Also, it follows, well, kind of easily that also this equality holds for nu equal to 1, 2, and 3. Well, this is obvious because, for instance, for nu equal 1, you have 2 over n less than this, and this is that 2k is less or equal than n. Well, this is true because this, okay. Also, the same happens for nu equal 1 equals 3. For the other inequality, let me think. We can work with the distance. For instance, for nu equals 1, here we have this. This is true because if you look at the graph and you look the distance, here is I plus 1 over n, and if you look distance, this is the distance between I plus 1 over n and t. This distance is less than 2 over n. And also the same happens for all the other values. For nu equals 2, here we have this, no? Here we have I plus 2 over n, and if you measure the distance, you have that this is less than 3 over n. Well, now we are give a certain bound for the over some intervals, over 3 intervals of the difference of this. Okay. Okay. Now, on this interval, we have this. The distance between the Brownian motion at I plus 1 over n and the Brownian motion at 1 over n is less or equal than 3 times j over n. And also on these intervals that are well, all these intervals are closed, no? You have 1 over n, I plus 1 over n, I plus 2 over n, and I plus 3 over n. So in this interval we have this, in the other interval, well, we have this, and in this other interval we have this. I'm going to show why this is true. Okay, I'm going to show why that's true. Okay, you can take h equal to e plus nu over n minus t. This h is between, you can verify that is between 0 and 1 over k. So under this event, if this event happens, if that event happens, what do we have? Remember the event ajk. The event ajk is where this happens for all h between 0 and 1 over k. So under this event, I am taking h like this. Okay, I am taking that h. So if you take that h, so you will have this, that the Brownian motion at t plus that h minus the Brownian motion at t is bounded by j multiplied by I plus nu over n minus t. Okay. So so we have this, no, that the Brownian motion at I plus nu over n minus the Brownian motion at t is bounded by j. Well, you can bound this with this 1 plus nu over n, and here we have 1 plus nu over n. Okay, this inequality is easy to see because I over n minus t is at most 1 over n. Okay. That this is because that t is in this interval, no, between I minus 1 over n and I over n. Okay, so we have this bound. Well, and we are done. This bound, this bound serves for nu equals 1, 2, and 3, and also for 0. Okay, and we have all these 3 bounds. Okay, well, but I was forgetting something. Here you have to use the triangular inequality. Okay, you have to use a triangular inequality. Here you can rest the Brownian motion key. Okay, just to give an idea, no, you use here a triangular inequality. Okay, and here we have this, and then you use this bound, this inequality. Okay, also here you use the triangular inequality minus wt más wt, and here minus wt más wt. Okay, so what's happening? Well, we are supposing that the event ajk happens if the event jk happens, these three inequalities happen, right? So if we define this set C and I like the intersection of the three events above, well, first we have this event is measurable by obvious reasons, and also we have this. Why? Well, if you look the construction, we have this, no? That if this event happens, you can take an integer n greater or equal than 4 times k. So this is arbitrary, the n is arbitrary. This is for all n. There exists an a, okay, between 1 and n, and here is for all n. For all n greater or equal than 4k, we have that there exists an a between 1 and n such that these three inequalities holds. So that's why we have this inclusion. Okay, that means that for all n greater than 4k, there exists an I between 1 and n such this happens. This is the three events. Okay, so we have that this event is included in an event C that is measurable, and that's good. Now, if we prove that this event has probability 0, so we are done with the proof, right? So that's the final step to justify that this event C has probability 0. And now I'm going to justify that. First note that these random variables, I'm going to do that here. These random variables are equal in distribution to this random variable. Okay, so using the scaling property, we have this. If you multiply by this square root of n, this is equal in distribution to square root of n multiplied by w at 1 over n, and by the scaling property, this has this is a standard normal random variable, right? Okay, so
okay, let me just point out that this choice of new varying from 1 to 3 is just for the computation to give the desired result at the end. Okay, so you don't need to necessarily to choose new varying from 1 to 3. This is chosen in order to give the desired result at the end. It's consequence of how the proof is.
You're asking me why nu is varying from 1 to 3?
Yeah, this is a choice.
Yes, it's a choice.
You want to put A inside some set. that has probability 0. So
This,
why have you choose 3 and not only 2 increments?
good question.
So this is for the computation to work at the end.
Yes, good, good question. I think that choice is done by on purpose, uh, in order to have that, in order to have a bound for the probability of C, a bound that tends to 0.
Yes, yes, of course.
Yes,
That's it.
I think that's the reason. It's on purpose. Mhm.
It was not a question. I was just pointing out that this choice, uh, which might seem odd, is to have the desired result at the end of the proof.
Okay.
That's exactly it.
Okay. Okay. Thanks. Thanks much. So, if we compute this probability, this is the, well, what's that? Uh, is the probability uh, of this, of the intersection of these events. Okay, but those events, those 3 events, if you remember, where I write it. Oh, okay. Okay. One even. Well, there are in 3 intervals that are not overlapping. So by the properties of the Brownian motion, no, that it has independent increments, we have that these 3 events are independent. So the probability is this product of this. Okay. But I'm going to multiply all of this by square root of n, and here square root of n, and well, here is a standard normal random variable. So there is a very known result, a very known bound for this probability. I'm going to use this. Okay. Mm, okay. So here we have this, no, the the probability of this. Mhm. Well, here we have this. Okay. So by this property we have this, no, this is less or equal than this.
Yeah. This is a consequence of the fact that the density
Oh,
of the normal, the standard normal distribution is bounded by 1. So
yes,
you
yes,
have,
yes, we are watching this, but you can bound by with this rectangle. uh, mm,
yeah, the height is not 1, but it's
yes,
1 of
yes,
2. square root of 2b pi b.
Okay. So this, well, this doesn't depend on nu. So here we have j power 3, and here we have n power 3 over 2, and here we have 3, 5, 7, and this is equal to this. Okay. So we want to show that the probability of C is 0, right? Okay. The probability of C is equal to, by definition, no, is this the intersection over all n greater or equal than 4k of the union over all I from 1 to n of these sets. Well, you can see that you can have this for all n greater or equal than 4k, all n. Okay. So, but we have a bound for the probability of these events. This is bound by this, the probability of Cni, and here we have this. Okay, but this sum, this fraction does not depend on I, so we have this, no? And this is equal to this. Okay. And this is happening for all n greater or equal than 4k. So the probability of C is less or equal than this for all n greater or equal than 4k. So this implies that the probability of C is 0. Well, because this is working as a bound by below of this, no? You can have this. And this is 0. Okay, so the probability of C is 0, and that was the objective, no? The event C is measurable, has probability 0. If C has probability 0, the event AJK has probability 0. Okay. And that's why the event V has probability 0. If the event V has probability 0, then the other event, this other event, has probability 0, and we are done, right? So we have proved that the Brownian motion is nowhere differentiable. If you have questions, you can do it. Thanks for listening.
Okay, thank you. It was good. You had still some time, but okay. No, it's 50 minutes. No. Sorry. Yeah. 5 minutes. Okay. Ok, então a gente tem agora o próximo a apresentar seria o Anderson, né?
Sim, sou eu.
A gente pode começar 10 horas, então?
10 horas, perfeito. 10.